Hey everybody, so here we have this Bestec ATX-300-12Z power supply that is exhibiting an issue. I featured this power supply in a recent video where I compared it side by side with a different unit that I recased, but the PCB and everything inside is pretty much identical. This unit here, since that video was made, I had done a recap on this thing. I replaced all the larger capacitors on the secondary, replaced the one large capacitor in the 5-volt standby area, and I also had to replace these primary caps, believe it or not, because they were actually bulging. Here's one for example. See right here? A little bit of bulge in the top of it. Hard to believe. And that's actually a Panasonic capacitor, which is actually a decent quality cap. But anyways, this unit it has working 5-volt standby, but it will not power up. The supervisor circuit appears to be working okay. The supervisor attempts to start the unit, however, the supervisor only attempts to start for about a half second or so. Yep, so 300 millisecond TPS 3510. We have a TPS 3510 in here. So 300 millisecond power good delay. So basically what it does is for 300 milliseconds it will attempt to start, and if it doesn't achieve power good by that time, it then does not illuminate the power good output, and also does not, or actually will turn off or quit attempting to start the unit. So we're working with this unit with the case cover off. As I've discussed in a prior video, doing this is not something I recommend you do unless you have really good knowledge of what's inside of these things, and you have good knowledge of working around, well, deadly high voltages, because there is over 300 volts DC in this unit when it is plugged in, as you'll see in just a moment. So what we're going to do is I'm going to plug this in. I'm going to use my ballast device here. This is something I made in a different video. What this does is puts this light bulb in series with this load. So if something bad happens with this load, it doesn't short out the main AC supply. And also this light bulb helps act as an inrush current limiter to slow down the inrush current to this unit, even slower than the built-in NTC thermistor would do. So that being said, we're going to plug this in. Let's get our meter ready here. And of course, I suggest using a quality meter for something like this. And definitely check out my other video on working inside of power supplies like this for extra tips that I suggest should you decide to do something like this. So anyways, we're going to go ahead and power this up. Alright, we are now live. So you might be able to see the fan in here is not running. And you might be able to see this LED is not lit. So for example, I am going to show some voltages here on camera. So first and foremost, we have over 330 volts DC in this unit. So we have 340 volts there roughly. So yes, very dangerous voltage inside these units. The sticker that's on the cover is not lying when it says there's high voltage inside here. Some people may think, oh, it's just your 120 volts, your 240 volts AC coming out of the wall. No, it's more than that. Yeah, as you can see there, 340 volts. Alright, so first thing I checked was to make sure, well, of course 5-volt standby is working. Now, this heatsink here is connected to the negative of this rectifier bridge here. This heatsink is connected to the case. So for example, if I put this lead here and I put this lead here on the case, you see we have about negative 170 volts DC And if I go from the power supply case to the positive of the bridge, we have positive 170 volts. That's because this unit employs a voltage doubler circuit that rectifies the 170 volts V peak power coming from our AC. It doubles that to about 340. So yeah, very dangerous stuff inside these units. You definitely want to use caution working inside of them. Alright, so test our 5 volt standby. We can test either, of course, the purple wire on the ATX motherboard connection, and we have 4.99 volts. Or if I test this diode in here, we have 5 volts exact. So the thing is, looking at this, you say, oh, the 5 volt standby is working fine. Well, is it? So for example, when this unit tries to start, what happens is the supervisor on pin 3, so pin 4 is PS on, that's coming from the motherboard. Now in this unit it goes to a little bit more circuitry. So basically what happens is PS on gets pulled from 5 volts to ground. It's actually shorted to ground, and that in turn tells the supervisor that there is a command for power on. So then in turn FPO is also pulled to ground, and through that you have a resistor and an opto-oscillator LED between 5 volt standby and this FPO pin. Okay, so in normal situations what would happen is this would pull low and the 5 volt standby rail would be passed through a 100 ohm resistor in this case, and through the LED, which lights up. You don't actually see it, but there's an LED inside of what's called an optocoupler or opto-oscillator, and that in turn shines light on a phototransistor, and that phototransistor then turns on. It acts like a switch. It closes and then allows power to pass in the auxiliary circuit, which is about 14 to 16 volts roughly, to what's called a PWM controller, which is down inside this area. And that PWM controller then in turn switches on and off the MOSFET on this primary heatsink, and that's what drives the outputs of the PSU. Alright, so for example, when I go from case ground, we'll use case ground for this since it's at the same potential as the secondary heatsink, and this way I'll free up a hand. I'm going to probe the meter on pin 2 of the opto-oscillator, which should briefly show about 0.4 volts roughly. It shouldn't be exactly 0. It should be about 0.4 volts briefly. And this one, in normal situations in a working unit, you would just see 0.4 volts about all the time when there's a call for power. Or in the case when the unit is in standby, this number will be about 5 volts because there's nothing latching on the circuit to pull it down and turn on the LED. Alright, so I'm going to go and demonstrate that now. Alright, so you saw it went down to 0 exact, and now we're at 4.33 volts. So something is definitely wrong here. We're going to let this unit discharge, which I'll show it discharging. And you heard that little noise there. You maybe heard it. I think that's actually the 5 volt standby IC that makes that noise, the flyback circuit. You actually hear it make that noise. Sounds like an old TV. Alright, so now we have about 11 volts sitting here. And if, for example, if I probe pin 4 of the opto-oscillator, we have about 20 volts there. So pin 3 and pin 4 is basically the connections on the switch, or the switch side of the opto-oscillator, the output side, on the circuit that sends power to the PWM chip. And if I briefly short that out, you see now it discharges down to basically nothing. Alright, so for example, I'm going to do this time, I'm going to put the negative of the meter back on the case, and this time I'm going to measure the output of the 5-volt standby. Come on, freaking thing. I like these probes because they have only a very small amount of metal on the very ends. However, it does make a bit more of a pain to get this thing to stay in place. But anyways, we got it there. So now I'm going to probe the 5-volt standby output to the motherboard. Now, in normal circumstances, this number should come up to 5 volts and remain at 5 volts. However, watch what happens with this unit here. So you saw how the 5-volt standby briefly came on to, you saw something and it went down to absolutely 0 and then up to 5 volts. Now, for example, I'm going to see what our auxiliary voltage is, and we can check that on pin 4 of the opto-oscillator. And for this, our negative, but the meter needs to go to the primary heatsink, as it's connected to negative of the optocoupler since we're working in the high voltage section. Now watch what happens here. We still have 18 volts there. Let me go ahead and ground it back out. So I'm going to apply power. So you can see how it too briefly went down to 0 and it came up. Definitely something up here. Okay, so for this one I'm going to demonstrate how I tested to see if the PWM controller is working. Now, the way I do this is I turn the switch on and turn it right back off. What we're doing is we're just charging up these capacitors here. We don't want to have AC onto this, just for this. We're going to jump start this unit and see it run for about a second. And the reason why I don't want AC power going into this, because we are effectively bypassing the short circuit protection and all the protections in this unit. So we don't want power going in the event that there's something wrong, because this thing would not shut down until I pull the meter probe off. So what I'm going to do is I'm going to pulse this on and back off, and then I'm going to touch this meter lead between pins 3 or 4 of the opto oscillator. And what that's going to do is that's going to short it on the outputs and bypass it and send power to the PWM controller. So anyways, here we go. So you heard the thing discharge, and you might have seen the fan run. So our PWM circuit is working, and the power supply actually did briefly start up for a moment. So what that means is either we have a short circuit in here that is pulling down the 5-volt standby and auxiliary power rails to ground, or we just have a very weak 5-volt standby rail. Because when any load is applied, it just pulls it down to ground. What should happen is when there's load applied on the 5-volt standby rail or load applied on any of these rails in this unit, the feedback circuit should tell, in this case with the 5-volt standby rail, should tell the IC over here controlling this 5-volt standby circuit to increase its duty cycle, to therefore apply more power to that rail to make it, to keep the output at 5 volts. However, that's not happening. Okay, everybody, so now I have my other unit, which is internally the same. This one here, although it does need a recap, it does power up. So we can use it as a good example here to compare to. So what I'm going to do is I'm going to do a couple of the same tests with this one. However, you'll see that this one fires right up. What I'm going to do is I'm going to probe pin 2 of the opto-isolator. Now, of course, unit is not powered up, although we have a little bit of residual voltage there from the last time this thing ran. Alright, so what I'm going to do is I'm going to power this on, and you'll see this unit will start. So you see we have about 0.42 volts there instead of 0. Since this unit started up, the Supervisor FPO pin is remaining in the low state, so because it's active low, therefore this unit is not only turning on, but it's staying on, and this circuit is being pulled down, and we don't have 0 volts. We have about 0.43 volts there. So, for example, if I power this off, alright. So for example, let's see what our primary voltage is. Okay, it's about 9 volts now. So what's going to happen, you're going to see it climb just a little bit, and then it's going to eventually start going back down. It'll go up to about 12 or 14 volts or so, and it'll start coming back down as the bleeder resistors in these caps discharge it. Okay, so this time what I'm going to do is I'm going to probe the purple wire on the ATX motherboard connection, and we should see this rail come up to 5 volts and stay there roughly. Okay, so now I'm going to see what happens with our auxiliary supply. So I'm checking pin 4 of the optocoupler. You see it comes up to about 14.6 volts. And now we're up to 18 volts about. That will eventually come down. Okay everybody, so for this portion of the video I'm going to load test the 5 volt standby rail on this unit, and the way I'm going to do that is I have taken some old USB ports from a computer case, an old computer case, and I have chopped off the motherboard connection off that cable, and I have more or less soldered the 2 different red and black wires together because it's 2 USB ports. I plan on using this for something later on. But what I've done is I soldered them together, and I've jammed the 2 connections into the purple and black wires so that both USB ports are getting 5 volt standby power. And I have connected up this USB powered desk fan, which is rated for 5 volts 0.65 amps. I'm not sure I can say it or not, but 5 volts 0.65 amps, which is well within the load capacity of this 5 volt standby rail. And if you have a listen here, the fan comes on and runs at full speed, from what I can tell. So what I'm going to do is I am going to probe the 5 volt standby diode, since that's what I have easy access to. You see we have 5 volts exact. Let's go and turn our fan on. It didn't even sag. So the 5 volt standby rail, at least as far as the 5 volt load goes, it seems fine. So for example, there I just hit this switch over here and I turn the fan on to put extra load on the 5 volt standby to drain this thing a little faster. You could probably hear how that screech was a little louder. That's because that switcher was having to, basically that chip, which also has a built-in switch, was having to work a little harder because the 5 volt standby had some load on it. Okay, so now I have green and black shorted, and I still had the fan connected up, the USB fan. I have it switched on. Let's see if this thing will start with some load on the 5 volt standby rail. It does. So the power supply is currently running. So I'm thinking what's going on here is we may have some bad capacitors in either this area or this area. So the power supply is currently running. You might be able to see if I turn this fan off. Power supply unit remains running. Now this time if I hit this light switch, fan is off. Unit does not start. But it starts up when I apply a little bit of load to the 5 volt standby rail, as you may have just seen. So it does look like a 5 volt standby rail regulation issue, sorta. Now, these units should start without any load connected to the 5 volt standby rail other than the internal loads of this PSU. It should not need extra help from more or less extra load from connected devices for this to start. Very interesting find. So again, power this up. Fan is turned off. When I turn this fan on, it adds some load to the 5 volt standby rail, and therefore it causes the switcher in the 5 volt standby to increase its cycle to drive up extra power or extra capacity on this 5 volt standby output and give this thing enough power to start itself. It's very interesting. So this is the first time this unit has ran on its own, well, figuratively speaking, without the help of this little bit of extra load on the 5 volt standby rail. But it means we are getting warmer on finding the possible issue. So what I'm going to do is I'm going to replace probably a couple of extra capacitors in here. So this is a diagram. I think this is my first time showing it here. I got this diagram off of badcaps.net from user Everell. He had it posted in a forum thread. So this is the diagram of the 5 volt standby circuit in the Bestec ATX-300-12Z power supply. So the 250-12Z and this 300-12Z internally are almost identical. The 300-12Z has larger heat sinks and has larger capacity on the secondary rectifiers, and I believe also has a slightly bigger primary switcher, slightly larger primary capacitors. However, the secondary capacitors and the overall board layout are identical. So more or less what's going on is we have our supervisor over here, which pin 3 is our FPO. That is connected through the optocoupler. This is actually on the cathode side, on the load side of the optocoupler, the ground side basically, you want to call it that. And before the optocoupler we have this 100 ohm resistor, which is tied to 5 volt standby. Okay. If the 5 volt standby rail isn't regulating properly, it may not have enough oomph to supply enough power to start this unit up. So if we come over here, this is what's in our 5 volt standby circuit on the output side. We have these two capacitors, C36 and C37, C36 is under the secondary heatsink, C37 is way over here. I'm actually kind of surprised. I didn't realize they were both part of 5-volt standby, but it actually makes sense. And of course you have D23, diode D23. So for example, diode D23 is right up here. Now this unit is currently powered off. It's been powered off for a few minutes now. It's right up in there. It's a big diode. So the two capacitors I think could be responsible for this are C46, which is located next to C36, right next to the secondary heatsink. Not sure you can see this or not. And it's a Capzon, which is, of course, a very wonderful brand. Yeah, a crappy brand. And also C50, which is right next to the primary heatsink and right next to our 5-volt standby switcher. Either of those two, I'm believing, could cause this problem, possibly C50. Now, it's interesting, C50 is the critical capacitor in the infamous motherboard killer Bestec ATX-300-12Z. That unit has a 2-transistor 5-volt standby rail, and when C50 begins to fail, the 5-volt standby rail skyrockets out of control. Now, the Bestec ATX-250-12Z, the Bestec ATX-300-12Z, and the Bestec ATX-300-12E, they all have this 5-volt standby switcher, which is an A6351A, which is an 8-pin dual inline package IC. It has both the flyback controller as well as the overpower and overcurrent protections, overvoltage protection, all that stuff built in. So it's a much safer 5-volt standby rail design. But C50, when it fails, it, in this case, does not cause the unit to go over voltage on the 5-volt standby. It just, I'm believing, is causing it to not be able to handle regulating as easily. So in other words, when there is load applied to either the 5-volt standby rail or the auxiliary supply, which is also fed by the 5-volt standby transformer, which is roughly 16 volts about. When any of those ask for extra load, this unit is not providing. But what's interesting is when you apply some load on the 5-volt standby rail, that is enough for this unit to start. As this unit currently is, I could probably throw it into a computer and it would start, because the computer's motherboard would have enough load on the 5-volt standby rail for this thing to start up. But again, these things should not require extra connected load on the 5-volt standby rail externally to power up. So anyways, that being said, I'm going to pull this PCB out and I'm going to replace those caps. Okay everybody, so I got the board pulled out of this unit again, and I'm going to go over the caps I'm going to change out. So I think I got one of the designators wrong earlier. Well, in this unit, that cap is actually next to the 5-volt standby switcher is C60. So we're changing out C60 and C46, which are 10 microfarad 50-volt parts. And I'm thinking one of those two might be the reason why this unit fails to run or start up without the 5-volt standby rail being loaded down some. Also going to change out C12, which is in the front of the unit. And it's also part of that feedback circuit for, I think this is a feedback for the PWM supply. We'll go ahead and change that cap as a precaution. I'll explain why in a moment. I could replace C13, however I don't have a 0.1 microfarad 63 volt part. I do have a 0.1 microfarad 50 volt part, and on the schematic, which I'll show you in just a moment, it appears that capacitor only sees the auxiliary supply, which, I mean, in the schematic has a 25 volt capacitor nearby on the same circuit. So I could probably get by with changing it, however I'm going to leave it. I'm just going to leave it be. Also going to be replacing C27. That's a small capacitor over on the 3.3 volt sense circuit in this unit. So I don't think I've shown y'all this yet. I may have shown you this one. This is a hand-drawn schematic I found on badcaps.net forums. Someone went through the effort to, and I think it's Everell, he went through the effort to hand draw this schematic of the Bestec ATX-300-12Z 5-volt standby circuit, and also included the supervisor and the PWM controller in there as well, and some other things. Very handy. And also, I found this. This is a full schematic of the similar Bestec ATX-300-12E power supply. Now, the Bestec ATX-300-12E power supply is really just a beefed up 250-12E with a fixed 5-volt standby circuit and the elimination of the minus 5-volt rail. Not much difference there otherwise. But even though this unit is slightly, the 312E has parts in different areas, the designators are the exact same from what I'm finding, so it's been very useful on this unit as well. Bestec seem to have kept using the same designators, meaning capacitor number 1, or like for example C1, C50, or C60 for example. They've kept using the same numbers on parts throughout the unit. So even though this schematic is not the exact same, it's been very handy. So I'm not going to bore y'all out too much with this. I'll show some footage of changing out one of the capacitors. So the reason why I'm changing out those 4, now I could do the 5th one as well, but I'm going to leave it. These 5 capacitors in this unit, in this specific one here, are Capzon. And Capzon is like the lowest of the low. Well, not really the lowest of the low, but among the lowest of the poorest quality capacitors Bestec used in their units. Capzon would be the worst. TPO would be right behind them. Jamicon, a bit better. Not the best, but better. Along with JPC-TUR. That you'll find in some of the older units from like 2001, 2002. This unit I think is from 04 or 05. Now if it had TPO capacitors in it, I could date it off the capacitors, but this one did not have TPO caps in it. But anyways, we're going to grab the caps and we're going to go ahead and start changing caps out. Okay everybody, so I decided to videotape the portion where I replace capacitor C12 because it's a whole lot easier to get to than the others. It might be a little easier to film. Although I can't guarantee I'll be able to get this on camera really well, but we'll try. So C12 is right there. Yeah, these little caps are hard to film replacing because they're so small and they're in such tight to get to spots. But what I gotta do is locate where it goes to the board, and it's right there. So I'm gonna walk it out of the board by soldering one side, lifting on that side, then going to the other side, soldering that, lifting on that side until it comes out. That one just came right out. So careful eyes might notice right next to where I'm working some fresh solder joints. That's because I replaced one of the transistors in this unit in this area just as a precaution, or just trying to troubleshoot why this thing would not start. And I had recorded video footage of that, but I'm not posting that because I was kind of just, like I said, it'd be boring to watch, I think. YouTube already seems to kill my videos due to low percentage viewed on some videos. But we got that cap out. There it is. 2.2 microfarad, 50 volt. So here's our new replacement capacitor, 2.2 microfarad, 50 volt. Alright, so I gotta clean these holes out. I want to try with that, see how it goes. Gotta clean those holes out so we can easily put the cap into place. Alright, so we push it through, we verified that it's in the correct direction. I'm going to fan out the leads. And then we're just going to go ahead and put fresh solder on all of these caps. There's 4 to do. Okay, so I'm going to go ahead and solder in these 4 caps. Okay everybody, now I've got these caps soldered into place. I'm going to use some flush cutters. And they're called flush cutters because they're real like shallow or just flush at the bottom. That way you can get up real close and cut the excess lead away right at the bottom of the PCB. It's good to leave about a couple or so millimeters of lead there. Also, it's very important that when you solder, you don't accidentally bridge connections because that can cause a short circuit. Now, there's some areas where it's okay to bridge, and that's when, for example over here, these 2 holes, or I should say, this hole and this component or this solder trace, there's all the same trace. Yet, for example, over here, that resistor, surface mount resistor, and this hole for the capacitor is part of the same trace. Yet over here on the other side, that trace is different from this trace. So it's definitely to keep that in mind when you're soldering. So make sure we don't have any loose bits of solder in here if we want to put this back together. Also want to check in the case itself. And this unit here has a piece of plastic that lays in the bottom between, of course, the metal of the case and, well, the PCB. There's actually a gap in there. Also, we have this standoff here. So that being said, we're going to mount this PCB back into place. Install our 4 screws to secure it into place. And then we're going to back porch test this unit, since we just finished doing some soldering work to it. Fingers crossed this time it will start up on its own without the need for some load on the 5-volt standby rail. Also, let's not forget to plug our fan back in. Okay, we are ready to back porch test this thing. Okay, so I got the unit on the back porch, and I'm of course using the safety ballast. Let's see what this thing will start. And it starts right up. There we go. So that's what it was. It was the little capacitors. And I'm thinking it was probably C60 that was causing our failure. So as you see now, the unit fires right up without the need for load to be applied to the 5-volt standby rail. So that's great. That's what we wanted. So we're going to shut this down. So you can see the green LED came on. That means that we achieved power good. So this thing's ready to power our system. Well, once we get it back together. So what I gotta do now is we're gonna let this thing discharge for a few minutes. That's all it really needs in this case. We'll put the needed zip ties back into place on the wires and for the like everything inside. Get everything buttoned up. Put the cover back on and it'll be good to go. Okay everybody, so before I put this video, I'm going to test one of these caps. This capacitor in my hand here is former C46. It was located next to the secondary heatsink. I want you to have a look at this. Now this old 1970s era capacitance meter does not measure ESR, but it measures capacitance. And I want you to have a look at this. This is supposed to be a 10 microfarad capacitor. Yeah, it's only doing about 3 microfarads. Yeah, that ain't right. Yeah, when these caps fail like that, it messes everything up. Alright, so this 1 microfarad cap, can't remember sure where it came from in the unit. We're going to see what it does. It's very important that we get the polarity right on this. So this is a 1 microfarad. So I say it's pretty close. Alright, here's my theory. So C46, there's our new one there. You see where it's at. It's right next to this heatsink. Now generally the larger caps with vents on them are the ones that tend to bulge and show visual signs of failure. And for years I would just change out those larger caps and slap it back together and put the unit back into service, but we have to keep in mind that these units are getting older. And it's probably getting time for those little caps to start failing. At least the ones that are exposed to heat. These are electrolytic capacitors, and when they're exposed to heat, they tend to dry out. And that's why they can fail without visual signs of failure. So there's C60 over there. I would test the I would test the old C60, but I damaged it getting it out of the board, so we can't test it. But I'm pretty sure it was probably doing the same thing or something very similar. So yeah, there you go. The little capacitors are important too, and with this unit being roughly 20 years old now, hard to believe it, 20 years old. Was 2005 really that long ago? With the unit being 20 years old, those little capacitors that are in hot spots, they're starting to go bad. So I think from here on out, when I do a cap job on one of these units, especially if it's a case where the unit is not working, I'm going to do all the large caps as usual, but I'm going to also replace those little ones. And in this unit, it'd be C46 and C60 and some others in there. So, as you see, that was it. It was capacitors, the little ones. So anyways, I'm going to slap this cover back on here after I zip tie this wire and I zip tie this bundle of wires here. Okay, so I got the cover back on it, and this one's ready to go back into service. Funny thing is, I have another one just like it. Same issue, probably same problem. I may feature this in a future video. So anyways, hope you enjoyed it. Thanks for watching.